Let's talk about how to use and interpret an equilibrium constant. First of all, the numerical value has an interpretation. For any reaction with a large equilibrium constant, defined to be roughly 1000 or 10 to the third power or larger, the numerator terms, the products, must be significantly larger than the denominator terms, the reactants. This means that the reaction described by this constant must have a much larger concentration of products than reactants at equilibrium. This is said to be a product-favored reaction. Conversely, small values for the equilibrium constant, defined to be below 10 to the minus third or 0.001, correspond to low product concentrations and high reactant concentrations at equilibrium. This implies a reactant-favored reaction. Equilibrium constant values can also be used to determine whether a reaction will proceed in the forward or reverse directions for any given set of initial reactant and product concentrations. To make such a determination, we need to use what's called the reaction quotient, or QC. The reaction quotient is defined in exactly the same way as the expression for K, except that the concentrations that we plug into the equation are not necessarily equilibrium values. What we can do with the reaction quotient is to plug in some arbitrary concentrations for the reactants and products for some set of conditions, determine the numerical value of Q, and compare that to the value for K. If Q is less than K, the reaction will proceed to the right. In other words, there will be a net conversion of reactants into products. If Q is greater than K, the reaction will proceed to the left, or in other words, there will be conversion of products into reactants. And finally, if Q and K are equal, the reaction mixture is already at equilibrium and no net reaction occurs in either direction. An equivalent way of thinking about it is this. If Q is less than K, the reaction will shift to equilibrium by increasing the value of Q until it reaches the value of K. To increase the value of Q, we can increase the numerator and decrease the denominator by converting reactants into products. Likewise, if Q is greater than K, the reaction will shift to equilibrium by decreasing the value of Q until it reaches the same value as K. This can be done by decreasing the numerator and increasing the denominator by converting products into reactants. Let's see how we can use equilibrium quantitatively. As an example, at 700 Kelvin, 0.5 moles of hydrogen iodide is added to a 2.00 liter container and allowed to come to equilibrium according to the chemical equation shown below. What concentration of hydrogen, iodine, and hydrogen iodide gases will be present once equilibrium is established? We're told that Kc for this reaction is 57.0 at this temperature. The procedure to make this determination is outlined here. Briefly, we first need to establish which direction the reaction will proceed. We can do this by computing Q with initial concentrations, comparing the value to K, and deducing the direction of the reaction. Next, we're going to make what's called an ice chart. Under the balanced reaction equation, we're going to make a table with 3 rows. The first row will have the initial concentrations, the second row will have the change in the concentration to establish equilibrium, and the third row will have our equilibrium concentrations. I for initial, C for change, E for equilibrium, hence ice chart. We'll use this chart to find the values or expressions under the equilibrium concentration row and plug them into the expression for K. We'll solve for the change in concentration for each reactant and product. It's possible that this might involve solving a quadratic equation, which would mean having 2 solutions. If this happens, we will need to interpret the results in context to choose which answer is correct. Once we solve for the change in each species concentration, we can find the numerical value of each concentration at equilibrium. Back to our example. Here's the balanced reaction equation and the ice table beneath it. Initially, there is no hydrogen or iodine present, so those have concentrations of 0 in the first row, initial concentration. Our initial concentration is the 0.5 moles of hydrogen iodide divided by its volume, 2.0 liters, both provided in the problem, so a concentration of 0.250 moles per liter initially for hydrogen iodide. Now we know that the equilibrium has to proceed to the left. Why? Because we have no reactants present initially, we can't shift any more towards the products. There are no reactants to convert into products, so the opposite must occur. Anytime one or more species has an initial concentration of 0, the reaction must proceed in the direction towards that substance, since we can't end up with negative concentrations anywhere. Now we don't know what amount of hydrogen iodide will be converted into the reactants, but we do know this. Because of the coefficients in the balanced equation, for every 2 moles of hydrogen iodide consumed, 1 mole of H2 and 1 mole of I2 will be produced. If we call the change in concentration of, say, H2 X, we know that this must equal the change in concentration of I2 as well, so that will also be X. And of course, the change in concentration of HI will be negative 2X. Negative because it's decreasing, and the 2 is from the stoichiometric relationship, the 2 in front of HI in the balanced equation. The third row of this chart, equilibrium concentration, just comes from adding the first 2 rows. For H2, we get 0 plus X is X. For I2, 0 plus X is X again. And for HI, 0.25 minus 2X is 0.250 minus 2X. We set up our equilibrium expression and plug in each expression and the value of the equilibrium constant. On top, we have the HI concentration, which was 0.250 minus 2X, quantity squared. On the bottom, the H2 and I2 concentrations are both X, so X times X is X squared. And of course, earlier they told us that Kc had a value of 57.0 at this temperature. Now we have an expression we need to solve for X. Since we have an expression squared over another expression squared on the right, we can simplify it by taking the square root of both sides. Glossing over the remaining steps, which are just algebra, we get a value of X equals 0.0262. Remember, X tells us about the change in concentration of the reactants and products. Our equilibrium concentration of H2 and I2 were both just equal to X itself, so both of those have a concentration at equilibrium of 0.0262 moles per liter. For HI, we found that we would have a concentration of 0.25 minus 2X, which gives us 0.198 moles per liter at equilibrium.